Hi, welcome, and thank you for showing an interest. Instead of doing a formal introduction, I will show you quickly some bits and pieces that I've been working on the last couple of months. And this also leads up to why I came at the idea at all. First off, a bit of procedural destruction real time. So this is not an animation, but if you throw a stick of dynamite in there, this happens. This is slowed down, and on the right is at normal speed. Another thing I did was like a cover system for NPCs to see cover and also to approach, advance or retreat. It was based on the GDC talk about Watch Dogs Legion. And an overkill solution for the nav agents, the Godot solution for avoidance. I couldn't really find my way in it, and I did an overkill solution by implementing a async compute shader to arrange that. And it plugs in, this is a 2D demo, it also works in 3D, of course. And the last two, in the bottom right, intentionally I omitted the audio, but I visualized it. It's real-time echoes, so it's not just a reverb effect, but real-time echoes in the landscape. In the top left, no decals for bullets, but also, again, real-time destructions. And holes in the wood are actual geometry holes, so you can peek through them. So how do I got from that to wanting a million trees? Well, like Emilio, CEO of Godot, always says, I'm not going to be the guy that makes GTA 7, so no need for a million trees. Small indie game developer, so small levels. But the thing is, if you have a small level, very small, 1 square meter, if you're standing there, you can still see in each direction for about, let's say, 5 or 6 kilometers. I wanted a bit of context. So on the right here, one of my levels, which looks kind of nice until you zoom out. And then you have this barren desert landscape. What I initially did was, okay, put some hills around it or some mountains, but then, yeah, it feels very boxed in. So hence came the need, okay, I wanted to show context, not necessarily an open world, but it would be nice if if you run at the top and you can see maybe the next level in the distance, something like that. So small levels, but a large map. It started out as a bit of a fun project. I allocated 2 days, and as any good developer knows, at the end of day 2, you look at the calendar and about 2 months or 6 weeks have passed. But the overall idea was 2 days. So I wanted to stick to a few things. No C++, no manual ROD stuff, meaning not going directly to the rendering server, etc. I wanted to stick to GDExtension nodes. I got some inspiration thinking about trees from Unreal, from animated foliage, specifically a tech demo they did for The Witcher. And okay, they use completely different technology. They do very high-tech, very fun stuff. I call it fun stuff, very interesting. My way around this, that we don't have that, is, well, not doing it. Which was a very good strategy, which was implemented very quickly. And I thought, okay, what could we do? And I thought, well, okay, what if I just make a voxel mesh? Think like a Minecraft version of my tree. And then I make a smaller version of that and a smaller version of that. And then use the respective APIs, array mesh, add service from array, to put them as normal Godot LODs. And what this interface does is basically, this interface is also being used if you just import an asset. You have this little checkmark, generate LODs. Under the hood, it also it uses some different code to actually make the LODs, but it's basically this API that it uses to create the asset, and that it works under the hood automatically. And I wanted to use that. It just works. We all know how that went, huh? Given the 2 months. Okay, so welcome to the most terrible idea ever. And why is that? A simple cube, let's call it a voxel, that's about 12 primitives. And yes, if you zoom out far enough, it becomes 1 pixel. So that's one heck of an expensive pixel to draw, right? And it's in 3D as well. So one is facing you, and if you're at a resolution of, let's say, 40 by 40, yeah, there's 40 others behind them. So 40 times 12 primitives for 1 pixel. Ouch. But that didn't stop me from trying, right? What we can say, and the end result is like that, performance-wise, this will never win from using alpha cards. So that's a lost battle. But that wasn't the goal. The goal was to have a nice experiment and gain some knowledge. And also, again, learn new things about Godot. The thing is about cards, though, it's not just about the number of primitives, because most people think cards perform so well because they have few primitives. It's just 4 vertices and you're done. But there's more to that. I'm not going to go do a deep dive. There's this video, maybe look it up sometime, and it goes in about AMD's RDNA architecture on the hardware actually. Same thing for NVIDIA, and they have a commonality. And it is that the GPU hardware rasterizer, they internally work when filling on 2 by 2 pixel cells, so 4 pixels at a time. So what happens, if you draw a very small triangle that's 1 pixel, it will still work on 4 pixels. It will just reject the 3 you don't use, but you're losing potentially 75 of the fill rate. And one of the reasons that cards perform so well is not only because it has few vertices, but the triangles are usually, except when really far in the distance, the triangles are big enough to benefit from the fill rate. And again, it's a very long technical video, but very interesting. I can highly recommend it. So that was kind of the bad deal. So, but maybe it's a good deal. What could we benefit? 360-degree correct silhouette, which is also kind of achievable with cards or imposters if you're using octahedral projection. But that's a lot more difficult, and I didn't really want to do that. And this seemed so much easier. Well, we're going to have correct shadows, basically. Self-shadowing, and that's kind of impossible using cards or imposters. And here we can win back some of that lost performance, perhaps. It's texture-free. Because the cubes, the faces, if you just use vertex colors, you don't need textures anymore. It's just a mesh with vertex data. And that means that if you draw a forest in the distance and you have 10 different trees and 5 different bushes, there's no textures to load. If you see them in the distance, no state changes when rendering, no samplers in your fragment shader. So yeah, the GPU can go like a Gatling gun on those things. So that kind of compensates for the loss in fill rate due to that other thing. Or so I hoped. Okay, so I had 3 steps to do. Populate with high quality, high quantity, convert the assets, and have things rendered. I used protonscatter. Huge shout out for the maker of that plugin. And if you want to do anything with LODs or want to experiment with behavior of multimeshes and multimeshes cut up in grids to see what it does for performance, this is the tool to use. Really, really nice, and it helped me a lot. I'll quickly cover what I did. Protonscatter is like a scatter tool, but it also contains things to quote-unquote render. It generates nodes that in turn are rendered by the rendering server. I made a custom renderer to plug in, basically a plugin on a plugin for protonscatter. Instead of directly rendering, I let it create so I capture the output and I create a resource, and then I wanted to make a little runtime to actually render it. This had the benefit that I'm not married to protonscatter now, because there's a lot of other really nice tools, Spatial Gardener, TerraBrush, etc. And I wanted to be like agnostic to the other plugins. Another benefit is I could take the composite, I could have one scene and use those tools, populate my level, Then I get the composite, and then I have another scene, which is your actual game, which is nice and clean, which just has the resource and runtime without having all of this tooling included. So for rendering things fast, you quickly wind up with multimesh instance, which has two, well, not issues, but behaviors. First of all, it's seen as a single mesh, so a single LOD selection. So, you know, if these stars, if they're close or further away in the back, they all get the same LOD selection. That's one. Second one is, yeah, everything that is in the multimesh instances that's outside of the screen still goes through the full GPU pipeline, so that's a loss. It won't draw the pixels, but you know, all the vertex data is still processed. So I thought, okay, to avoid these two things, let's do subdivision based on distance. So you see a lot of bots, they're not NPCs, but just a bunch of trees. So basically, in the distance, you have a multimesh with 1,000 trees. It subdivides in like 250, and so on. And closest by, change over to measures this 3D. This is not something spectacular. There's a lot of other plugins that do kind of similar things. Drawback is, yeah, you need a ton of GPU data, a ton of nodes, because for all the LOD, all the subdivisions, if you have, I needed to have about 5, which goes from 1 kilometer to 50 meters. And then, yeah, you have an explosion of nodes. And no matter how you do it, it's slow to load and create. To load, it's slow because of the amount. To create, it's slow, even with direct rendering server calls if you wouldn't use nodes. And it adds up very quickly. If we want 10 assets for 4 biomes, you get tens of millions of nodes. Not feasible. So then I thought, okay, this looks a lot like from the top, like a quad tree. Extend that to 3D, you get an octree. Again, like Spatial Gardener does a similar thing. But I wanted to take it one step further and basically only feed the rendering server what's inside the camera frustum. Well, easy peasy. Let me show you what that looked like. So now you can see in the distance the red boxes, as they get more near, things get more fine-grained, and that works. This is a little hop forward, just to keep the pace up, because time is flying by. I could also change the settings. And this turned out to be very important for two things. This is like fine-tuning for culling opportunities for the rendering server, but also, you know, where the cells switch from LOD level to prevent pop. So easy peasy, right? Only I didn't want to use C++, and this was actually, doing that takes quite a few iterations, literally, you know, for loops, a good bunch of math. So I started with 22 milliseconds, ouch, for static geometry. And after some optimization, I got, yeah, depending on the scene, 2 to 6 milliseconds. So I needed to do something about that. I wanted to get below 1 millisecond. I had a few options, separate render thread, several known bugs. So, okay, scratch that one, I wanted to avoid it. Nodes are not thread safe. The common ways around it for faster math and iterations is, oh, okay, go native. I didn't want to do that. Instead of using nodes, using the rendering server API directly, well, again, overkill. You lose a lot of things that are done for you automatically. So, and it doesn't help speed up the math. So what I came up with was this. In the main thread, the update camera, I send that to a worker thread, and that triggers the worker thread to start actually working. It creates a delta. I'll touch on in a second in the next slide. And your game logic runs, and only at the end, it gets all the computed stuff. And all that the main thread needs to do is do an execute. And what that means is basically update a few nodes. And because it's a delta, it's only the stuff that's moving in and out of the screen. So the state delta generation looked like this. it's being recorded. I'm going over it really high level and quickly, so I'm not going to read everything. But basically, it intersects with the frustum. It drills down on the high level of detail cells, on the octree cells, but only where there is actually content. I match that to the data using Cantor IDs, which is basically a bit encoding to see if there's data. So you get a bunch of intersections. I apply the acid rules because a small bush draws less far than a tree, that kind of stuff. And then I split the data into near and far sectors. So do I want to have real trees that are mesh instances, or is it like a bunch of trees or a forest in the distance? That gives us a state. Remember the old state. And again, we're in the worker thread, right? So basically you have the whole frame to compute. So that worked. We do a diff, and what you wind up with is basically a command stream towards the main thread. The main thread, it picks up that delta. It also resets the delta. And that's very nice, because what happens is, if for some reason you change the view and it's like quite a lot of data, and the worker thread is late, then the delta will be reset by the last query. The new one isn't set. So FPS is not impacted. You'll just see a little fringe on the side of the screen. It's a different trade-off. But you don't get like real big bounces in the FPS. Works really nice. Anyway, we have this delta. On the main thread, I pass this delta to two nodes in my little runtime, a near renderer and a far renderer. Sounds very heavy, renderer, but really, the code almost fits on the screen because it's really simple now. Basically, everything that is added, all it has to do is set a transform and some item data, like a visibility range for mesh instance, or the actual transform buffer for the multimesh. And anything that goes out of the screen is removed. It's basically, node.visible is false. Done. And put it back in the pool. To add a pool so that you don't have to instantiate any instances, which improves performance a lot. And also the pool doubles as a cache. So if you look left and right, everything is already set up. And it becomes really, visible, true or false. That's all the main thread has to do. So that's very quick. So that's how I got the main thread to be below 1 millisecond. One thing to note, the built-in profiler doesn't really like if you have a worker thread. It's completely fine with it, but for the frame time, you need to just ignore that and look at the GPU profiler. And it becomes very hard if you have a problem in your main thread that's eating a lot of time. It's more difficult to spot because it accumulates all the time as process time, even though it's on a worker thread. So that's one thing I ran into. And you can see here, frame time 8 milliseconds, but it's only one call because my main thread was basically idle. And all the time actually came from my worker things. Okay, how to get voxels. I'm going to speed up a bit, given the time. I used an orthogonal camera and on a sub-viewport. And instead of moving the camera, I just used a very small Z-near and far difference. So the draw distance is like a slice. And it works the same like, one of those medical scanners that scan your brain slice for slice that you see on TV. Same thing. So scan, tuk. Well, do that 12 times. 6 times for each direction, so you get the 6 faces of the cube. Why 12 times? You need the albedo, the color, but also you need the normals, because otherwise it will really look, it really will look like Roblox or Minecraft, and we want to have a bit more detail. One issue I ran into is, for some reason, there was more bark than leaves, and if you look on the left, that's not the case. What was going on there? There was like a small bug in my tree shader, and it had to do with mip-map compensation for alpha scissor threshold without going into what that is exactly. But basically, if you see it in 3D, it caused this, a bit exaggerated, and that was also happening in my orthogonal camera. Once I fixed that, problem solved. How to get faces? Well, you just get the texture from the viewport, twice the voxel resolution, so that you have 4 pixels per face. And so, okay, so now we have a face with 4 normals and an albedo. This is important to have high detail voxel information, because even though it's only 1 pixel, in an ideal world, yes. But with the LOD system selection mode from Godot, you can see that in the center of the screen, if you go to the corners, the object becomes larger. So yeah, there's not an exact match with 1 pixel. Sometimes the voxels will show up, and the better they look, the better they look. Without going over the details, I used worker trap pools a lot in the tooling to generate the voxels. Saves a lot of time. A really nice API. I don't know who ever invented that in Godot, but have to love that person. Again, I'm speeding up a bit. The bottom line is worker trap pool, great thing, and that allowed me to the initial voxelization, to do that for your average assets in about a second. A little over a second. Really nice. So what do we get? At this stage, we have like a high-res version, which is horrible for performance because it's twice the geometry of the original. But it's the starting point to downsample our LODs from. One thing to note, basically technically we don't have voxels. We have 6 point clouds of faces that together form something that resembles a voxel. And we saw the same thing if you zoom in the Unreal thing. Kind of the same thing happens. It's different, but same. So LOD generation. Well, easy peasy, right? Bit of downsampling, you do the same thing as you do in 2D to 3D. Well, that was a little bit more involved than I thought. First, let's have a look on what it looks like. In the beginning, it's quite slow, and that has to do with occlusion culling. I'll cover it in a second. Do they both run? Yeah. So this is superimposed on the original meshes. And the one on the left is an interesting case, because due to the aspect ratio of that mesh, yeah, it's not really suitable for cards. If you make a card of that from the side, it looks great, but then you do an area view and you see a small strip. Voxels don't have the problem. I left out the top and bottom to make it more visible. So that's what it looks like when it's happening. Okay, occlusion culling. Of course, when you put a lot of voxels together, or faces together, there's going to be a lot of stuff that you actually can't see. Normally, if you put 2 boxes against each other, sorry, I did it again, eh? If you put 2 boxes against each other, the middle, the intersections you can just reject. That's a very easy algorithm, but we can do that because, again, it's like 6 point clouds merged. There is a cohesion, but you're not sure which faces are there or not. So I needed a perceptual approach. I used raycasting, which takes quite a bit of time to set up and to perform. So that's why the initial version is like there in a second, but then the process takes a bit of time. But again, worker trap pool is your friend. So where are we at now? Putting all of this together. Hopefully you don't feel this in your stomach. The first time I saw this clip on my monitor, I was a bit like, whoa. But if you look especially in the edges of the screen, there's a lot of popping and dancing. I need to look at this screen because I'm starting to... Maybe I'm very sensitive to that. Now if you look at the bottom right, over the top right, you see this dancing. So what was going on with the dancing? Because the trees looked a bit like doing the chicken dance, And as it turns out, I examined a few screenshots. Basically what's happening was this. The yellow being the underlying geometry that triggered voxels or faces to be generated. Yeah, sometimes they fall on an edge, it becomes 1 or 2. That doesn't matter in itself, but it does when you use both odd and even-sized voxel resolutions. So really simple fix, only use the odd sizes so that there's always a center, and then they stopped moving left and right and up and down. There was a lot more going on. Colors, normals, the volume of the shape, voxel aspect ratio, really a lot. So yeah, it's more difficult to see on this screen actually than on this, but you see kind of wavy, you see banding. That was very difficult to get straight. So all of these aspects, all of these quantization steps, it took a lot of work and a lot of investigation. But I wound up with this, which is a lot better. At the end, of course, you see quite a clear band, but that's the biggest step. If you go from 2 pixels to 1, yeah, that's the biggest change in volume. You know, there's no way about it. To compensate for volume, I had to do something. You can't change the shape, but what I could do is actually space out the voxels a bit, and that gave much better results. Except for one thing, which also led to compensating using aspect ratio. And the next slide will show that. It's a bit dark, but on the right is with square voxels, and just making the voxels smaller. And on the left is volume compensation, both with making them smaller, but also changing the aspect ratio. And that looks a lot better. Now it's a closed shape again. So, a bit later. This is also, I think, 3 times the amount of trees that I had in the other scene. I think this is like 2.5 million. And it's still there, but it's a lot better already. And of course, due to the spherical selection mode, my talk yesterday about LODs, it's most noticeable in the peripheral vision, but you know, in the center where you're looking mostly, it looks, well, half decent. It has a different look than cards. So one more trick with voxels. Again, texture free. And that allows us to do something else. And that is just bake the highest level sectors, so the ones that are far away. Because if you have like 10,000 trees in a sector that's like this big on screen, it may be like 20 trees become 1 pixel. And you can do some math, and you can just merge these pixels. That also allows that if you have like 20 different trees or 5 different color flower fields, you can just compress that to 1 single mesh, which draws, of course, much faster, because that prevents for those distance sectors to have like 15 draw calls for 15 multimeshes. One of the things, when I was kind of done, all of a sudden, you can see there were some floating trees in the air. And that got me puzzled a bit, and I started debugging, and you find nothing. Everything seems fine. But actually, it was just a terrain LOD system. It's just a terrain 3D, also a nice plugin. Because if you zoom in, you'll see that the terrain starts forming below the tree. Suddenly, it gets a base. So that was a bit of a gotcha. A bit of light response, because that was one of the things that I was after, better light response than cards. Play it again. And it does a pretty decent job at that, I think. So in conclusion, good timing because I'm at the last minute. Now, GD scripts and nodes can take you, with a bit of creativity, can really take you a long, long way. Yeah, it can sometimes make you do things. You can do things that you wouldn't think possible without going native or doing other fancy stuff. The overall architecture that I now have, I think it really shines. I can change things really quickly for the threading model, which LOD system to use, because I also have a little check mark, use cards, and then it changes to cards. So really nice. One thing that is missing is colliders, but hey, that was not my initial objective. As far as the voxel LODs go, okay, the light and shadow response is really nice. Pretty good in the medium to long range, which is nice for, the long range vista that I wanted to have. At closer range, yeah, the performance was quite lacking, I must say. I did get to about 60 FPS at HD, but that's, you still have the rest of the game to put in as well. Voxels visible in the corners, like cars, it has a certain look. And a discrete LOD pop. Every now and then you'll see a bit of like swimming. But that's maybe solvable. I have ideas about that, but no spoilers for, well, maybe a next talk on a different time. So in general, cards and imposters remain the common go-to. But I thought it was a nice experiment, and it gives me a lot of new knowledge about how Godot works. And things like, with the threading, that the profiler, it works. But it has some implications, and it becomes more difficult to profile your main thread issues. So that's about it. The future, who knows? Because I honestly don't know, so this was just a thought I had. Maybe this will have a kind of a comeback with ray or path tracing. Because I don't know what happens if you ray trace or path trace a card with your fancy octahedral projection. I don't know. I really don't know. And maybe then voxels will fare better. Okay, thank you.